Yeah, so today we're welcoming Michelle Avataneo from Northwestern to talk to us about morality. So it's 1 hour for the main talk, Michelle, and we'll have clarificatory questions during it. So over to you.
Okay, thank you very much for inviting me, and any feedback, comments are very appreciated. So the title of the paper is The Evolutionary Success of Moral Universalism versus Moral Particularism. There's a lot of words in the title. So let me begin by explaining how I think about morality and what are universalism and particularism. That didn't work. So in interaction with others, human behavior is shaped by psychological constructs that motivate individuals to value more than just their individual material payoff. I refer to these psychological constructs as moral principles. They're also commonly referred to as moral values or simply values. To make sure we're on the same page, let me give you an example of morality at work. So suppose we have two people, Alice and Bob, and they're playing a game. Their fitness payoffs, which represent anything that's material, such as effort and nutrition, are represented in this table. If Alice and Bob only interacted once, this is a prisoner's dilemma game, so the only equilibrium would be defect-defect. But what if Alice also values Bob's fitness payoffs? If Alice cares for Bob, she would get extra utils from taking the action that for each of Bob's action makes Bob best off fitness-wise. So if Bob cooperates, 1 is larger than -1. So if Alice cares for Bob, she would get extra utils from cooperating when Bob cooperates. If instead Bob defects, 2 is larger than 0. So again, Bob would be better off if Alice cooperated. So she would get extra utils Y from taking the action that makes Bob better off cooperate. Alice's moral principle then is the X, the Y, and their placement in the matrix. So that's morality. What about universalism and particularism? Particularist moral principles depend on whether an agent's opponent is in her in-group or in her out-group, whereas universalist moral principles do not depend on who an agent's opponent is. So an example of a particularist moral principle would be, say, care for the in-group and spite for the out-group. So if we had Bob with that moral principle, what would be going on in Bob's head when he's matched against an in-group individual is that Bob will be getting these extra utils from cooperating against the in-group individual. But when Bob is matched against an out-group individual, instead what would be going on in Bob's head is these utils for defecting, because he wants to hurt the out-group opponent. The moral principle, again, is the X, the Y, the X prime, the Y prime, and the placement in the matrix. So that's particularism. And what's an example of a universalist moral principle? Well, for example, care equally for everyone. So if Alice had the exact same utils against the in-group and the out-group, she's caring the same for everybody. So that's an example of a universalist moral principle. So that's how I think about morality. That's what I mean with universalist and particularist moral principles. What do I do with this? In this paper, what I seek to answer is what is more likely to prevail in society, universalists or particularist moral principles? To answer this question, it is useful to know where morality comes from. It turns out that morality is at least partly genetic, and thus it is subject to evolutionary forces. So how do we know this? Because what looks like moral behavior has been observed in several social mammals, like monkeys, elephants, vampire bats, and young humans, months-old babies already exhibit protomortal behavior. Moreover, monozygotic human twins are more morally similar than the zygotic twins. What all of this suggests, at least to me, is that the morality that prevails in society is the morality that survived an evolutionary process. Now, there is something important about evolutionary success, and it is that it is highly dependent on environmental conditions. So think, for example, of plants that are evolutionarily successful. The plants that are evolutionarily successful in environments with little sun and lots of water, like the jungle, are very different than the plants that are evolutionarily successful in environments with lots of sun and little water, like the desert. So what I do in this paper is identify an environmental condition that affects the evolutionary success of universalist and particularist moral principles. Using evolutionary game theory, and in particular using the indirect evolutionary approach of preferences, this paper shows that in environments that promote short-lived interactions with different people, say like cities, universalist moral principles have an evolutionary advantage, whereas in environments that promote long-lived interactions with the same people, for example, rural areas, particularist moral principles have an evolutionary advantage. Now, this is the main result of the paper, but the analysis tells us more. It tells us that the world would look something like this. So the blue areas represent areas where there's short-lived interactions, and green areas, environments where there's long-lived interactions. We see the main result I just told you depicted in this figure. So we have universalist moral principles in areas where short-lived interactions occur, like for all. And we have particularist moral principles in long-lived interaction areas. But there's more that can be seen in this figure. It is also the case that in short-lived interaction areas, there is coexistence, there can be coexistence of different universalist moral principles, but that's not the case in areas with long-lived interactions. There's a unique particularist moral principle. There's more that the analysis tells us that cannot really be seen in the figure, and it is that because of the way universalists behave and of the way particularists behave, there will be more cooperation against outgroup opponents in areas with short-lived interactions, but there will be more relative moral payoffs from prosocial behavior in areas with long-lived interactions. So that's kind of what the analysis in the paper shows. I am making two key assumptions to get to these results. I will discuss them later, but let me just mention them briefly right now. The two key assumptions are that moral principles are observable. This is obviously a simplification, but I believe it is plausible in interactions in which, even if the interaction is one-off, one can talk and observe a person prior to choosing actions. The other assumption is that I assume that an agent's in-group is the set of opponents that have her exact same moral principle. This comes from the observation that humans associate with individuals that have similar values in preference to individuals with similar visible characteristics like race and ethnicity. Now, this second assumption is not necessary for the main result of the paper. It will change some of the implications of the result, but it does not change the main result. Now, before I jump into the model, let me just briefly tell you what I believe the contributions of this paper are. So I think the main contribution of the paper is a conceptual contribution. It is to provide a theory grounded in evolutionary game theory that explains the universalism-particularism divide observed in practice. And the second contribution is methodological. In this paper, I introduced a novel solution concept to predict what morality emerges from evolution, which I call evolutionary advantage. The standard solution concept is evolutionary stability, but it is too weak in the sense that it is not sufficiently predictive. Evolutionary advantage refines the predictions given by evolutionary stability. Okay, so that's the motivation. Let me then jump into the model. Now, the model is very long. There's a lot of parts, so let me just give an outline of what I'm going to do. First, I will describe the game agents play repeatedly within a generation, where moral principles are taken as given and determine equilibrium play. After I do that, I'm going to describe the transmission of moral principles across generations, and I'm going to describe the solution concept I use to predict what moral principle emerges from evolution. So within generation, time is discrete and infinite. In every period, a continuum of agents are paired to play a 2x2 game with actions that cooperate and defect. With probability P, a pair remains matched in the next period. With probability 1 minus P, the pair splits and both agents are rematched uniformly at random in the population. So in a society, in an environment when P is equal to 0, agents will be having one-shot interactions every period. In societies with P is equal to 1, agents will be matched with the same person throughout their life. Agents have a common discount factor beta. I only have this common this discount factor for technical reasons. So I'm going to think of B as being very large, close to 1. The parameter of interest is delta equal to P times beta. But again, I'm like mostly thinking the variation is coming from P. I will tell you later exactly where I need the beta. Agents seek to maximize their utility, and their utility has two components. It has fitness payoffs and moral payoffs. So what I'm going to do in the next 2 slides is explain each of these components of the utility. Fitness payoffs are captured by the fitness matrix pi, which has a corresponding fitness game. So let's say if at period t, there were both agents that are matched effect, each of them gets a fitness payoff of t that period. Without loss of generality, I assume that A is larger than or equal to D. That's just a labeling. With loss of generality, the fitness game is either a prisoner's dilemma or a hooked-up game, and cooperation is efficient. So I'm going to focus on games in which if the opponent cooperated, what would maximize fitness is to the effect, but what would maximize the sum of the fitnesses is if both agents cooperated. Every agent in the population has the same fitness matrix, and mixed strategies are denoted by sigma. So the fitness payoff of an agent playing sigma t against an agent playing sigma prime t is simply this. So that's the first component. The second component is a little bit more complicated. It's the moral payoffs. The moral payoff of an agent will depend on her moral type, on her opponent's moral type, and on the fitness matrix. The set of all moral types is denoted by capital theta, and each moral type is characterized by its associated moral principle. So the moral principle of an agent of moral type theta is a function, M, that will map the opponent's moral type and the fitness matrix to a 2x2 matrix. And moreover, it's going to be a function by parts. So it will apply an in-group subfunction that maps the fitness matrix to a 2x2 matrix if the opponent has the exact same moral type, and it will instead apply an outgroup subfunction if the opponent has a different moral type. So the moral payoff at time t of an agent of time theta playing theta t against an agent of time theta prime playing sigma prime t is simply going to be this. I know this is a little bit abstract, so let me give an example of moral payoffs.
Can I ask a question?
Sure.
So how many types are present at every moment in time?
I'm going to assume 2. So it's only incumbents and mutants at a given moment of time.
Okay.
Okay. Now, throughout the slides, whenever I give an example, it will always be the same fitness matrix and the same fitness game, which is this prisoner's dilemma game. So suppose we have this, and suppose Bob is of a moral type theta, and the moral principle associated with theta is this, so care towards the in-group and spy towards the out-group. There is green here, and this is just to remind you that you already saw this Bob in the first couple of slides. The moral payoff Bob gets if matched against an in-group opponent will be this. So recall we have the X here and the Y here. These are simply 3 in this particular example. The moral payoff Bob gets if matched against an out-group opponent would then be this. We have the X prime here and the Y prime here. They're now 3. So, okay, so that's the moral payoff. Now, what are strategies? Agents observe the moral type of their opponent. And a strategy for an agent of moral type theta is going to be a series of functions, one for each period, each of which map the fitness matrix, the type of the opponent, and the history of that interaction into a mixed action. For technical reasons, strategies are assumed to be of finite complexity in the sense of Galai and Stanford. That is, agents only play strategies that are implementable by finite automaton. I will tell you where exactly I use this assumption later. Okay. Now that's the strategy. So what's the utility? So the utility at a given period t of an agent of type theta match against an agent of type. Sorry, did somebody ask something? No? Okay. Well, the utility at time t of theta match against theta prime, when they choose those strategies at time t, is gonna simply be the fitness payoff at those chosen strategies plus the moral payoff at those chosen strategies. Agents seek to maximize the present value of their expected utility, which is simply this. So for a type theta match currently against a type theta prime, this would be the expected utility in her lifetime with that opponent. And that's the continuation payoff. So this W would be the present value of the expected utility when matched with a randomly selected opponent. The reason why I need a beta that's not 1 is because if I had beta equal to 1, this term would explode. Now, I assume agents observe only the history of their own interactions. So if they're matched with a current opponent, they do not observe what that opponent did in other past interactions with other agents. So there's no reputational effects. Since the probability of being rematched with an opponent one was matched in the past, but the interaction ended, is 0 because there's a continuum of agents, it is optimal for an agent to choose her strategies but by maximizing just her current expected utility with the current opponent. So when theta is matched with theta prime, it's optimal for her to just ignore any future interaction with other people and just focus on maximizing here. If the interaction ends, when it ends, then the agent would choose the strategies that maximize the interaction with that opponent. And how do agents behave? I'm going to assume that agents play a Nash equilibrium. So an equilibrium strategy for an agent of type theta, gamma star theta, prescribes an optimal response for a given opponent of type theta prime, given the opponent's equilibrium behavior. This is just the normal definition of Nash equilibrium. I'm just going to stop in case somebody wants to read it.
So that presumes that I know all the strategies that every type follows, right?
Yes, so your best response to the strategy, yes.
Right, good.
Are we going to get quite a few Nash equilibria here, or?
Yes.
Okay, thank you.
Yes, there's multiplicity. Okay, so players of the same moral type are assumed to adopt the same equilibrium strategy against each opponent type. So not only they have the same utility because their moral principle is the same, they also choose the same thing. And again, one does not follow from the other because there's multiplicity of equilibrium. So, okay. Now, sorry, that was all about the behavior of agents within a generation. So that's the game. I already explained what agents are doing. Let me now tell you how I formalize a universalism and particularism. For a given pi and delta, theta is a universalist moral type if the in-group and the out-group subfunction output sufficiently similar matrices such that when they are added to pi, they induce the same best response correspondence. Theta is instead a particularist moral type if the matrices that are outputted are sufficiently different as to when added to pi, they do not induce the same best response correspondence. So let me give you an example of this. So again, this is our fitness. This is the induced fitness game. Suppose interactions are one-off. And let Bob be the Bob we already saw that have this particularist moral principle, care and spite. The moral payoffs that Bob was getting was this towards the in-group and this towards the out-group. When we add them to pi, we get this. So this is the utility towards the in-group, and this is the utility towards the out-group. These have very different best response correspondences because towards the in-group, Bob has a strictly dominant strategy to cooperate. 4 is larger than 2 and 2 is larger than 0. Towards the out-group, Bob has a strictly dominant strategy to defect. 5 is larger than 1 and 3 is larger than -1. So this means that theta is a particularist moral type. If instead we had Alice, and Alice had a moral type theta prime, which was care towards the in-group and care towards the out-group, but a little bit more care towards the in-group, this would be the moral payoffs. Alice would get towards the in-group, towards the out-group. When we add it to the pi, we would get this utility towards the in-group and towards the out-group. Now, even though these two functions are different, they are not sufficiently different as to generate different behavior. Alice has the same strict best response towards the in-group and out-group. So Alice has a strictly dominant strategy to cooperate towards the in-group and also towards the out-group. So theta prime is a universalist moral type.
So it's universalist for this game. Yeah.
Exactly. So everything I do is for a given game and a given delta. So the delta also would affect whether you are a universalist or a particularist.
Okay, thank you.
Mm-hmm. Any other questions?
I had a quick question, if I may. So if somebody cares just a little bit, and for instance, if their function is care a little bit for the in-group and be spiteful for the out-group, it might not tweak their preferences for the in-group to cooperate. And so it would look like they would be willing to defect against both the in-group and the out-group. Would that make them universalist or particularist?
If they have the same best response correspondence, that would make them universalist. So even though it grants spite, if it is not sufficient to really switch your behavior, I say that's universalist.
Okay, so you're looking at kind of the ultimate payoff matrix and not the actual.
Yeah.
Okay.
Yeah, that's right. So it depends on the utility, really. And that's why it's dependent on pi, because I'm checking this. And it's also dependent on delta, because your strategies will depend on delta. So even if it's the same pi, you could be if delta increases, you might become a particularist because there's more strategies. So you have more options. So what you do with one or other might differ when delta increases.
All right, thank you.
Mm-hmm. Any other questions? Okay, so that's, I told you within a generation what agents are doing, how they're playing. I formalized universalism and particularism. So I'm about to move on to explain how moral types are transmitted across generations. But before that, let me just briefly discuss the two key assumptions I am making. So I am assuming observability of moral types for all probabilities of interactions, even when interactions are one-offs. I'm focusing in this paper in interactions in which people can observe and talk to each other before choosing a strategy, even if the interaction is one-off. So I'm thinking, say, of interactions what would have with an electrician, a plumber, a contractor, even if it's a one-time job, you would interact with the person. You would observe the person and talk to the person before you choose the action. There is evidence that in these sort of interactions, when people can observe and talk to each other, moral values are at least partially observable. So in individuals interacting for 10 minutes or more before playing a one-shot prisoner's dilemma can predict to a large degree of accuracy whether their opponent will cooperate or not. Moreover, individuals can also predict whether or not others are altruistic by watching videos of those others telling a story.
So, sorry to interrupt again, but you only need to know whether they're your type or not, right? If you treat all outgroup the same, would that?
Not really, because you have the same utility towards your outgroup, but your action depends on the other's utility as well.
Okay.
So outgroup can be different.
I see. Of course, yes, it's equilibrium. Thank you.
Okay. Any other question? Okay, so that's the first. The second assumption is that I assume that an agent's in-group is the set of opponents who have the exact same moral type. This comes from the following observation. So people often gravitate towards those who have the same values. Even in the 60s, when discrimination was not so terrible, shared moral values tended to outweigh similarities in race and ethnicity when forming associations and friendships. Moreover, racial discrimination decreased when information about moral values was revealed. So to me, this suggests that similarities in moral values is a very strong proxy for an in-group, whatever an in-group is for a person. Now, the main result is unchanged to alternative in-group definitions. Okay, so that being said, let me now move on to...
Can I say something here? You seem to be saying that, okay, you are a universalist if you're basically, you have the same pay of mate, you have the same best response correspondence across all other types, but then you're being very, so this is quite nice. I like you allow for a lot of things to be like universalist in terms of behavior, but then even if my value, you have 3, care 3, and I have care 3 and 2.9, then we're different in terms of this, right? So I'm out group to you because I have just slightly different.
Yeah, I see your point. Yes, you're right. I am doing that. I don't believe things would change if I would weaken it a little bit.
Yeah, exactly.
I would have to do the analysis, but I don't believe it would change that much if I weaken a little bit. But yes, you're right.
Right. But I think that it would be nice if it was more like consistent with allowing similar behavior or something like that.
Yes, I agree with you saying.
Yeah.
Yes. Thank you. Okay. So let me now move on to talking about transmission of moral types across generations. A given generation contains two things. It contains a distribution of moral types that tells us who the people in the generation are. And as I already kind of said before, I'm going to restrict attention to generations with at most two moral types. So there's going to be, at a given generation, only an incumbent or mutant, incumbents in proportion 1 minus epsilon. But again, these two, while I restrict attention to at most two types, these two types can be any type. Now, the second thing generation contains is a Nash equilibrium profile. There might be multiple Nash equilibria. So this Nash equilibrium profile tells us what is the Nash equilibrium, what are the equilibrium strategies agents in the generation are playing against each other. So I will denote it by gamma star, so that gamma theta star theta prime is simply the equilibrium strategy that a type theta plays against a type theta prime. I am going to measure the success of a moral type in a given generation. So for a given pi, beta, p, epsilon, and gamma star, by what I call the type's generational fitness. And the type's generational fitness is going to be this thing, this expression here. This looks a little bit horrible, but it is not. What this expression is the average per period fitness payoff an agent of type theta has in her lifetime. So this weight here is simply in a lifetime of capital T periods, the expected number of periods that the agent will spend in the little teeth consecutive interaction against somebody. And this is simply the expected fitness payoff in the teeth consecutive period in an interaction with somebody. So this is the fitness payoff in the teeth consecutive period against an incumbent, and that's the probability of being matched against an incumbent. This is the teeth consecutive, the period, the teeth consecutive period against a mutant. This is the probability of being matched with a mutant. We multiply this by the weight and we sum it across the teeth. We get the expected total fitness payoff an agent gets in her lifetime of T. If we divide it by t, we get the per period fitness payoff. And we take the limit because time is infinite. There's some things to mention here. So one, here's where I use the assumption of agents playing only strategies implementable by a finite automaton. So if I did not have that assumption, it could be the limit did not exist. So the assumption guarantees that the limit exists. Second, this would reduce to familiar objects in some cases. So when p is equal to 0, this thing would reduce to the one-shot fitness payoff. When this p is equal to 1, this simply reduces to the average criterion, which is used in the literature. And then last thing to mention is that if we want an interpretation for this object, what we could be thinking is that what's going on is that people are interacting, they have these infinite lives, and then nature draws uniformly at random one period, and that's the period that reproduction occurs. That would be the expected fitness of type theta in such uniformly drawn at random time period. Okay, so with that being said, intuitively, moral types that produce higher generational fitness in generation n would be overrepresented in generation n+1. And what we're interested in is in the moral types that survive the evolutionary process in the long run. So what's present here? I often say selected by evolution. What I mean with selected by evolution is simply what's present in the long run. Okay. Rather than modeling the dynamics of transmission, I use a static solution concept to predict which types are more likely to emerge from evolution. The standard solution concept used in the literature is evolutionary stability. Let me give you the definition of evolutionary stability I use in this paper. It is the definition put forward by Dekelili Gilankaya 2007, but specialized to populations with two types. So given pi and delta, a moral type theta is evolutionarily stable if there exists a Nash equilibrium strategy such that for every mutant theta prime, there exists an epsilon lower bar such that for all epsilon sufficiently small, and for all strategy profiles in which theta continues playing against theta, what she was playing, prior to the entry of the mutant, it is the case that theta gets a larger generational fitness than theta prime. Intuitively, a stable type is resistant to invasion. So once it's established in a generation, it cannot be displayed by the small scale entry of an alternative type. No matter if it's already established, theta is already established, no matter what mutant enters and what equilibrium is played, theta will get a larger generational fitness. Now, the thing is that evolutionary stability is too permissive, in the sense that there's too many moral types that are evolutionarily stable. So in particular, for all delta, there exists both universalist and particularist moral types that are stable. Now, I believe that there is a natural way that makes sense to refine the predictions given by evolutionary stability, and it is to also use the following notion, which I call annihilation. Given pi and delta, a moral type theta annihilates a pair, a moral type equilibrium pair, theta prime gamma star, if for every epsilon and for some Nash equilibrium profile in which theta prime continues playing against theta, what it was playing prior to the entry of pi, theta gets a strictly larger generational fitness than theta prime. Now, while evolutionary stability captures a type's ability to resist invasion, annihilation reflects a type's ability to invade. Because what's going on is that we have theta prime gamma star, theta enters in a small proportion. If there will exist an equilibrium in which theta will get a strictly larger generational fitness. So next generation, it would have spread at the expense of theta prime playing gamma star, but it continues getting a strictly larger generational fitness for all epsilon. So next generation, it would have continued spreading and so on until theta would have completely taken over. Now, intuitively, how does adding annihilation to stability refine the predictions? So suppose that for a given pi and delta, we had two types that are evolutionarily stable, orange and greens. And suppose that the first humans in the world happen to be blue, which is double prime plane gamma star. Also suppose that orange annihilates the first humans, but green does not. What would this mean? Well, it means that if we start with our first generation of humans, and there's a mutation towards orange, orange annihilates. So what this means is that next generation, orange would have spread, and it continues getting strictly larger generational fitness, so it will continue spreading next generation until it takes over. Now, orange is stable. So once it is established, the entire population is orange, no matter what mutant enters, the mutant will not be able to take over. It would be died out or stay in a very tiny proportion. So the population would continue being orange forever. That means that orange will be selected by evolution. If instead we have a mutation towards green, what would be happening is that green does not annihilate blue. So it will enter, but it will not displace blue. Next generation, we will continue having blue, and we will continue having blue. And that's it. If we were, since green is stable, if we were to get to the point in which the entire population was green, no mutant would be able to displace, and the population will be green forever. The problem is we cannot get to the point in which the population is entirely green. Now, if we took only
Can I ask a question?
Sure.
So, do I understand correctly that this assumes that the equilibrium is being played that makes it the definition of evolutionary stability or annihilation be satisfied, right? There might be other equilibria.
Yes, so for evolutionary stability, it has to be that in any equilibria, the orange is getting larger. Fitness payoff. For annihilation, that's right. There exists one equilibrium in which that happens. So I'm assuming that here, orange, it is always that equilibrium that's being played. Any other question? Okay. If we only took into account stability, we would predict orange and green emerge from in an evolutionary process. If we take into account annihilation, we would predict orange comes out of evolution. So that's how this annihilation is refining the prediction. The last thing I'm going to do before telling you the results is giving you the solution concept. So what the solution concept I'm using is going to put together evolutionary stability and annihilation, and it's going to apply to sets of moral types. The reason why I want a concept that applies to sets of moral types is because I am interested not in what individual moral type emerges from evolution, but whether the type or types that emerge have certain property. That is where there are universalists or particularists. So here is the solution concept. Let omega denote the set of all possible moral type equilibrium pairs. Given pi, delta, and s, a subset of omega, and given two disjoint sets of moral types, A and B, let calligraphic A denote the set of moral type equilibrium pairs in S that are annihilated by some evolutionarily stable moral type in A, and let calligraphic B be the set of moral type equilibrium pairs in S that are annihilated by some evolutionarily stable moral type in B. The set of moral types A has an evolutionary advantage in S over the set of moral types B if calligraphic A is a superset of calligraphic B, and a strict evolutionary advantage if calligraphic A is a strict superset of calligraphic B. So what this is telling me intuitively is pick any moral type in S, moral type equilibrium pair in S. If there exists an evolutionarily stable type in B that annihilates it, there also exists an evolutionarily stable type in A that annihilates it. Moreover, if the advantage is strict, besides that, there exists some type in S that can be annihilated by some stable moral type in A, but cannot be annihilated by any stable type in B. So what I interpret from this is the following. So suppose all moral types in A share a property, say universalism, and all moral types in B share a different property, say particularism. What I'm going to interpret here is that if A has an evolutionary advantage over B, the property that is shared by the types in A is more likely to emerge from evolution than the property that's shared by the types in B. Okay. Any questions about this?
So yeah, so it's basically that you'll have some target set S then. Is that going to be something in particular, or?
It's going to be any finite set of omega. So I'm going to show it in the result.
Okay, great. And okay, well, I'll wait until I see it.
Any other question? Okay, so let me give the result. There's two. So the first theorem tells us that for any pi and for any finite subset f of omega, a finite moral type equilibrium pairs f of omega, there exists this delta lower bar, delta upper bar, such that for all delta sufficiently small, the set of universalist moral types has an evolutionary advantage in F over the set of particularist moral types. For all delta sufficiently large, the set of particularist moral types has an evolutionary advantage in F over the set of universalist moral types. Moreover, for infinitely many of these finite subsets F, the evolutionary advantage is strict. That's what theorem 2 tells us, that for any pi, there exists infinitely many finite subsets F and corresponding D and the upper bar, the lower bar, such that for all delta sufficiently small, the set of universalist moral types has a strict evolutionary advantage in F over the set of particularist moral types. And for all D sufficiently large, the set of particularist moral types has an evolutionary advantage in F over the set of universalist moral types. So let me tell you something here. So the reason why I need F to be finite and not say something infinite, say omega, is technical. So what's going on is that for any moral type equilibrium pair you find, you will be able to find a delta below which universalists have the advantage and a delta above which particularists have the advantage. That is, whenever a stable universalist annihilates, so does a stable particularist. The thing is that to say that universalists have an evolutionary advantage, what you would need is a uniform delta below which any moral type that is annihilated by a particularist is also annihilated by a universalist. The thing is that these deltas are dependent on the moral type. So to get the uniform bound, we need to take the infimum. To get the uniform upper bar, I need to take the supremum. But the problem is that if the set is infinite, so if it was omega, the supremum would be 1. Because while for every moral type equilibrium pair, there is a sufficiently large delta, there will exist another that is like even closer to 1 and another that is even closer to 1 and so on. So to avoid that supremum equal 1, I am doing this finite set. Okay, I don't know if that makes sense, but okay, so that's the main result. And let me just, I don't have a lot of time left, so let me What I want to attempt to do is give an intuition of what's going on, but it is more, I'm not sure if it's an intuition or a sketch proof what I have. But what I'm gonna try to do is to explain what's the mechanism. Okay, so this is pi plus m of theta. So suppose this is the outgroup utility function a type theta has. So it's parameterized by this. This is the fitness game we had always had. What I'm gonna try to do in this slide is show what are the properties that these parameters have to satisfy to make theta stable. Okay, so to make theta stable, what needs to happen is that the agent with type theta has to not play certain strategies. A type would be stable if it can make the agent of that type avoid cooperating when the opponent defects. Because when an agent cooperates and the opponent defects, the opponent gets 2, and that is larger than the maximum an agent can get against her own type, which is 1. So we need to avoid that. What are the properties that E, F, G, and H have to satisfy to make theta stable? So first, we will need, ignore this to our difference. So we need G larger than or equal to E. Why? Well, suppose E was strictly larger than G. What would happen is that a mutant, which is the column, comes and says, okay, I'm gonna mix, but I'm gonna play with a very high probability cooperate. What does the column think? Well, E is strictly larger than G, I'm gonna cooperate. But that would give a mix between these two, and that would give the opponent something larger than 1. So to avoid that, we need G larger than or equal to E. The second thing we would need is H strictly larger than F. If F was larger than or equal to H, clearly the effect cooperate would be an equilibrium, so the opponent would get 2, then the opponent would invade. If interactions were only one-off, that's all we would need. But interactions could be repeated, so we need more. We also need G larger than or equal to F, because if not, again, a mutant could arrive and say, okay, I'm gonna mix here. If you do not cooperate every single period while I mix, I'm gonna cooperate forever, and you're gonna get G. But if G is less than F, then this guy would obey that threat, and that would give this mix that gives more to the opponent. We also need, for the same reason, H larger than or equal to E. If not, again, the opponent can say, I'm gonna mix, you're gonna cooperate. If you don't do that, I'm gonna play the effect forever, and that's gonna give you H. So to avoid the agent following that threat, we need H larger than or equal to E. We need these others, but I'm not gonna mention them because I'm not gonna use them. So we need this. Now, if you're a universalist, if theta was a universalist, we would need even more. If you're a universalist, what this means is that whatever equilibrium you pair against your own type would also be an equilibrium against any other type that plays the same strategy. So if you do not cooperate with your own type every single period, a mutant that comes and mimics you against yourself, so plays to you whatever you're playing against yourself, but does cooperate every single period against her own type, would get strictly larger generational fitness. So to be stable, a universalist moral type needs to cooperate every single period. But given these restrictions to do that, what needs to be the case is that E is larger than or equal to G. So that gives us that for universalists, we need this equality. And now for particularists, for them to not be observationally equivalent to a universalist, we need G larger than E. So that's kind of the properties that need to be satisfied by stable thetas. There's two very important things to note about universalists, and it is that they are indifferent between playing cooperate and defect when the opponent cooperates. So E is equal to G. And the second one is that they really do not like to defect when the opponent cooperates. So they would rather have the opponent defect when they defect than to have the opponent cooperate. That is, H is larger than or equal to G. We get this because there's two options. H larger than G, then obviously H is larger than G. The other option would be G larger than or equal to H. but G larger than or equal to H, we also need G equal E, and we also need H larger than or equal to E. So that means these two have to, this equality has to hold. So H is always larger than or equal to G. What's going to be the case is that for annihilation, when delta is very close to 0, this property here is useful for annihilation, and this property does not affect annihilation. But when delta is large, this property does not affect annihilation, but this property hinders annihilation. So for annihilation, what we need is the opposite that for stability. What we would need is to make our agent, the rho, get larger fitness payoffs than the opponent. So we need, if we get the agent to get 2 some periods, that would allow the agent to annihilate the opponent. So what we need is to get the agent to place this some period. Now, when delta is 0 or close to 0, there are two sort of equilibria that can accomplish this. One is if the opponent cooperates and our agent mixes between cooperate and defect. That would be a mix between 2 and 1, so that's larger than 1. The other option is the agent defecting and the opponent mixing. That would get something potentially larger than 1. Universalists have G equal to E. So for the first one, it is a best response for universalists to mix when the opponent cooperates. So they can sustain this, and thus they can annihilate any opponent that's willing to play with them this. Particularists will never do that. Because G is larger than E, they strictly defect. So they would not be willing to do that. For 2, both of them can sustain that against any opponent that would be willing to play with them, because G is larger than this and H is larger than that. So both would be willing to play that. So universalists can annihilate any opponent that particularists would, and more. No particularists would be able to play this, but universalists would. Now, when delta is large, when delta is close to 1, this changes. Because when delta is large, we again have these two possibilities where the rho can get something larger than 2, but there's a third one, and it is this sort of coordination. Now, when delta is large, again, universalists have G equal to E, so they will be willing to mix when the opponent cooperates. But now particularists would also be willing to do that because they can be threatened into it. So the opponent would tell them, you are going to mix between these while I cooperate every single period. If you do not do that, I'm going to defect forever. If G is larger than H, the particularists can be convinced into doing that. So now particularists would also be able to annihilate opponents that are willing to play this. For 2, they again are, if it works for theta 0, it works for theta larger because they can just repeat the stage Nash. So both of them can continue annihilating any opponent that's willing to play this. But now we also have this third thing. And what this third thing is doing is that, okay, the column is coming and saying, we're going to do this. We're going to coordinate some periods. We're going to cooperate and defect, others defect cooperate. If you do not do that, I'm going to punish and I'm going to defect forever. And that's going to give you H. For particularists, since G can be larger than H, they can be threatened into doing that. But universalists cannot, because for universalists, H is always larger than G. So that threat would not work against a universalist. But that means that particularists can annihilate everything that a universalist can annihilate and more, because they can be threatened into this sort of equilibria. Any questions about this? Okay, so that's the intuition, and then I think I just have like 3 minutes left. So let me just very fast give you the other implications of the theory. So another implication of this result, and really the analysis, is that in environments with small delta, agents cooperate more with outgroups opponents. Why? Because in environments with small delta, we have universalists. And remember, universalists are indifferent between cooperating and defecting when the opponent cooperates. This means that there can be an outgroup opponent that's cooperating every single period, and it would be an equilibrium for the universalists to also cooperate every single period. So an equilibrium in which the universalist cooperates against a cooperating outgroup opponent exists. That's not the case with particularists. Particularists for large delta, particularists strictly prefer to defect against an outgroup opponent. So no matter if the outgroup opponent is cooperating every single period, there does not exist an equilibrium in which the particularist would cooperate every single period against that outgroup opponent. So we would see more of this cooperation in areas where delta is low. Now, in environments with low delta, we would also may see diverse moral principles coexist. This is stemming sort of from this cooperation thing. Again, universalists are indifferent. So you could have two different universalist moral types that are cooperating against each other and cooperating against their own type. That would mean that they would get the exact same generational fitness. So they would be able to coexist. That is not the case with particularists. Particularists, to be stable, they need to get a larger, strictly larger generational fitness towards their in-group than what their out-group opponent gets against them. But that means that if you had two different particularist moral principles, they would not be able to get the exact same generational fitness. So you will not get this coexistence. And finally, in environments with small delta, it's also the case that agents get lower relative moral payoffs from prosocial behavior. So because of this indifference of universalists, what this tells us is that the moral payoff that they get from cooperating minus the moral payoff they get from defecting when an opponent cooperates cannot be too large. It is pinned down by the fitness matrix. It has to be exactly something that to achieve indifference. That is not the case with particularists. For particularists, since they can behave differently towards the outgroup and in-group, towards their in-group, they can get an arbitrarily large moral payoff from cooperation versus defection, and that will continue being stable. So there is more of these relative payoffs for their small delta. And that is it. I had some connections to empirical evidence, but I don't have time to that. So let me just go to conclude, which is simply giving a summary. What this paper does is apply the standard concept of evolutionary stability and introduce the notion of annihilation to predict whether universalism or particularism is more evolutionary advantageous. It shows that the answer depends on delta. In environments with low delta, universalists have an advantage. In environments with high delta, particularists have the advantage. The paper also proposes a theory of the world that matches, or at least is not refuted by empirical observation. I did not get to go over the empirical observation, but if you're curious, you can look at it in the paper. So it tells us that environments with one-off interactions, such as market settings, have more cooperation with strangers, that environments with one-off interactions, such as cities, have more moral diversity, and that environments with repeated interactions, such as rural areas, have higher happiness, if happiness is defined in a certain way. And that's it. Thank you very much.
Thank you very much.
Any feedback or comments will be very appreciated.